Hi, everyone. I'm Shamik Chaudhary.
Hi, I'm Shantanu Jha.
We work in the Equus group here at MIT, and today we're going to tell you about our project on quantum control via constrained trajectory optimization. So it turns out that many of the techniques we've discussed in class have broad applicability outside of robot dynamics, and one such area we were pleasantly surprised to find is quantum mechanics. Here, the state of a quantum system can be described by a complex vector psi, and the dynamics are given by the Schrödinger equation. Here, H is a matrix known as the Hamiltonian of the system, and it can be split up into this bare system Hamiltonian, which encodes the physics of the problem and the system, as well as a set of control fields, for instance, a laser pulse applied to an atom. In quantum optimal control, we often want to prepare some desired state or set of states. And this can be formulated as a trajectory optimization problem, essentially going along a given trajectory in state space. We can either transfer a given state to another state, or transfer a basis of states to another basis of states to enact a gate. And in this work, we focus on the first. We want to do this subject to constraints such as normalization and control limits on the drive amplitude and bandwidth. As you can see, we have linear dynamics and nonlinear constraints. And so we want to find a solver that is compatible with this problem structure. As an aside, I'll finally note that we can map between real and complex matrices using the following isomorphism, since real matrices are easier to work with standard solvers. So in class, we've touched upon many formulations of trajectory optimization. Usually they look something like this, where we want to minimize some cost function along the trajectory, subject to the dynamics, as well as a set of constraints. Methods for solving this include both direct methods like direct collocation, where both the states and controls are decision variables, or indirect methods such as ILQR, where only the controls are decision variables. In this work, we explore ALTRO, the Augmented Lagrangian Trajectory Optimizer, which combines both direct and indirect methods. Essentially, ALTRO is an ILQR solver, plus an augmented Lagrangian framework to incorporate the constraints, plus a so-called projected Newton method, which projects a rough solution to the problem into the constraint space to get very good constraint validation. Building upon Julia tools that already exist, we develop a package called QControl for numerical simulation of quantum optimal control. So the simplest system that we wanted to test our package on was the two-level atom, or the qubit. Here, the state space is a two-dimensional complex space. And so state vectors will look something like this, where the two complex amplitudes alpha and beta have norms squared to 1. Now, because of the normalization constraint, we can alternatively parameterize the state using the numbers theta and phi, which essentially map the state space of the qubit onto the set of states that live on the surface of a sphere. Physically, we can model the control of the two-level atom via this Hamiltonian, where Fq is the qubit frequency, and this is the bare system Hamiltonian, and A of t is the control field. If we look at the bare Hamiltonian dynamics, we see that it induces a precession about the z-axis at a frequency Fq, as evidenced by these 3 animations.
To demonstrate the utility of the package we've developed in this final project, QControl.jl, let's look at the optimal control of this qubit system. Here, our goal is quantum state transfer, going from the 0 state to the 1 state in the single qubit system. Our physical intuition tells us that if we drive this system at a frequency equal to the characteristic frequency of the qubit, then we should be able to drive transitions between the 0 state and the 1 state. If we look at the cost function associated with this problem, then we see that it boils down to a penalty on the amplitude of the controlled drives. The constraints, however, are a bit more interesting. The first of which says that we must satisfy the dynamics of the system. The second says that we must start in the desired initial state and end in the desired target state. And finally, we want our states to be normalized at all times. If we look at the optimized trajectory produced by our solver, then we see that we indeed do go from 0 to 1. Moreover, we can explain the precession in this trajectory by considering the base dynamics of this system. Next, if we look at the ALTRO generated optimal pulses, we see that there is a dominant frequency component at 5 gigahertz, which is equal to the characteristic frequency of this qubit system and consistent with our physical intuition. Finally, if we look at the projection of our quantum states along this z-axis, versus time, we see a trend from 1 to -1 as expected. And the smoothness of this trend suggests that the pulses we've produced are optimal. Next, let's look at a more interesting example of quantum error correction. In particular, let's look at the binomial code and state preparation in this code. Quantum error correction involves redundantly encoding 1 qubit of information, i.e. a 2-dimensional code subspace within a larger logical state space, which can be realized using, for example, multiple physical qubits. And in such an implementation, we can demonstrate the quantum repetition code, where a 0 logical state is equal to the 0 state in all the physical qubits. But this requires a lot of qubits and a lot of hardware. So alternatively, we can use the infinite dimensional state space of a quantum harmonic oscillator. And to define a 2-dimensional code subspace, we will use bosonic quantum error correcting codes, the simplest of which is called the binomial code, where the logical 0 is a superposition between 0 excitations and 4 excitations, and the logical 1 is equal to 2 excitations. And these excitations can be, for example, microwave photons in a superconducting cavity. Our goal here is another quantum state transfer problem, going from 0 excitations, i.e. the vacuum state, to our binomial logical code states. This has applications in quantum computation, quantum communication, quantum metrology, and quantum simulation. Now we can visualize the optimized trajectories for this quantum state transfer problem by looking at the Wigner quasi-probability distribution of our states versus time. And as researchers in the field, we can tell you that we were pleasantly surprised by how by these pulses. Moreover, I should note that using ALTRO on bosonic code control problems is novel work explored in this project. Finally, to summarize, we used ALTRO solvers on quantum optimal control problems and demonstrated some use cases in 2-level qubit systems, as well as towards the optimal control of binomial codes. Outlook in future work includes implementing techniques such as robust control, quantum gate synthesis, and including experimental realities such as loss and dissipation. QControl.jl will soon be published on Julia's general registry, which is like Python's PyPy. So we encourage you to check it out, play around with it, and you can also find our code at this GitHub repository. Thank you so much, and please don't hesitate to reach out with any questions.